In this video, we're going to do some extra examples that use Bayes' theorem and or tree diagrams. So let's jump right in. So in this first example, we have an experiment that consists of selecting two cards from a standard deck, one after the other without replacement. Okay, and what we're going to do each time we select a card is note whether or not the card is a heart. Okay, so we only care about hearts. So I'm going to let H1 be the event that we get a heart on the draw one. Okay, so the first time we pick. And H2 is a heart on the second pick. Okay, because we're doing one after the other without replacement. So the tree diagram for this is just going to be, so my first pick, okay, so I'm going to have, card 1, and I only care if it's a heart or if it's not a heart. So I'm going to call it H1 and H1 prime, or complement. And then I want to pick again, and again note if I get a heart. So I either get a heart or I don't. So I'm going to have H2 or H2 complement. Okay, so this is for card 2. Now I want to put the probabilities on, so here's where this without replacement comes in. So the probability I get a heart on the first draw, there's 13 hearts and 52 in total. This is 1/4. So if I don't get a heart, there's 39 non-hearts out of 52. This is 3/4. Now once I've drawn a heart, okay, so I know I got a heart. That means the 13 is now down to 12 because I didn't put it back. So the chances I get another heart are going to be 12 out of 51. So there's 12 hearts left and 51 cards in total. Now the chances I don't get a heart, I picked a heart, so the only card removed was a heart. So there's 39 other cards and 51 in total. So the chances I don't get a heart are 39 over 51. Now, if I did not get a heart, on my first draw, then there's still 13 hearts left. So the probability I get a heart on the second draw is going to be 13 out of 51, whereas the probability I don't get a heart is now going to be 38 out of 51. Okay, so that's our tree diagram. Now, it's nice to check, but each time we branch out, these probabilities sum to 1. Okay, so they do here, so that's good. So now we want to answer some questions involving this tree diagram. So what's the probability we draw 2 hearts? So this is the probability that H1 and H2 happen. So that means that I'm going to get both H1 and H2, which only happens on this top branch here. So we multiply along the branches, so this is going to be 1 over 4 times 12 over 51, which happens to be 3 over 51, which is approximately 0.059 if you prefer decimals. Okay, what if we want the probability we get exactly 1 heart? Okay, so that means that we either got a heart on the first card and then didn't get a heart on the second card, or we did not get a heart on the first card, but we did get a heart on the second card. So let's highlight these. Okay, so H1 intersect H2 complement is going to be we did get a heart, but then we did not get a heart. H1 complement intersect H2 means that we did not get a heart, but then we did get a heart. So those two pass there. So again, we multiply along the pass. So this first one is going to be 1 over 4 times 39 over 51. And then the second one here is going to be 3 out of 4 times 13 out of 51. And if you compute those together, you should get 13 out of 34. So 13 over 34, which is approximately 0.3824. Okay, So far no conditional probability, just a tree diagram, just using it in different ways. Now, part D. Given that, so now we know something. So the second card, the second drawn was a heart, okay? So H2 happened. What's the probability the first card was not a heart? So here we're looking for the probability of H1 complement given H2. Okay, so if we use our conditional formula, that's H1 complement intersect H2 divided by the probability of H2. Now we already did the top one, so it is in fact the blue path. Okay, now H2, what we want to do is look for every place where H2 occurs. So we want to multiply along those paths that end with H2. So, and we add different paths. So this first one, the top one here, is 3 over 4 times 13 over 51, so just like we had. And then if we do the pink, so one of the paths is the pink path that we already did. So that's 3 over 51, and the other one is this path again. So 3 over 4, 13 over 51. So if you compute this, this is going to be 13 over 68 divided by 1 over 4, which simplifies to 13 over 17, or 0.7647 approximately. Okay, one more of these. So given that we drew at least one heart, what's the probability we drew exactly one heart? So here we want the probability of exactly one heart, given that we got at least one heart. So we use our conditional. So exactly one heart and at least one heart, or intersect, divided by the probability of at least one heart. So when are both these things true? Well, if I get at least exactly one heart, then I definitely had at least one heart. And I need to get exactly one heart. So this top is actually just the probability I get exactly one heart. And to compute the bottom, I'm going to do the complement, so 1 minus the probability of no hearts. So this is going to be exactly one heart we already did. So we know the top is 13 over 34. And the bottom is going to be 1 minus no hearts. And no hearts is the only path we haven't done yet. So it's this bottom one, H1 complement, intersect H2 complement. So 3/4 times 38 over 51. And if you simplify that, you should get 13 over 15, which is approximately 0.8667. Okay, let's try another one. So, a box has 5 working light bulbs and 2 defective light bulbs. Okay, so that's going to give us 7 bulbs total. Okay, and we reach into the box and we select a bulb at random, and then we test it. Okay, if it's defective, so if it doesn't work, we're going to discard it and try another bulb, and we're going to repeat this until we eventually find 2 working bulbs. Okay, so the tree diagram here is going to be a little bit different. So the first thing we're going to do is pick a bulb. Okay, it's going to work or it's going to be defective. Okay, so this is bulb 1. Okay, now we continue until we find 2 working ones. So both of these paths are going to continue. Okay, and each time I'm going to find either a working one or a defective one. So this is going to be bulb 2. Okay, now if I get 2 working ones like I have in this top branch, I'm going to stop. Okay, now also the box has only 2 defective ones. So there's not an instance where I can get more than 2 defectives. So if I see 2 D's, then I know I can't get any more D's. So in this path here, I have 1 working, 1 defective. I still can keep going. Okay, so I'm either going to get a working one or a defective one. In this path, again, I have 1 of each, so I keep going. And I either get a working one or a defective one. Now in this last path, I found both defective ones, so I know for certain that I'm going to get a working one next. Okay, now in this path here, I see that I have 2 working ones, so that one's going to stop. And in this path here, I got 2 working ones, so I'm not going to pick any more there. And in all the other paths, so here I have 2 defectives, here I have 2 defectives, here I already had 2 defectives. So my next pick, I know I'm going to get a working one each time. Okay, and for all of these, that's going to be when I stop, because I've now found 2. So I may have to go to 4 bulbs. Okay, now I want to add probabilities. So in our when we picked our first bulb, there were 5 working ones and 7 total. So the probability we got a working one was 5 out of 7, and the probability we got a defective one, 2 out of 7. Now if we picked a working one, the probability I got another working one, there's only 4 left out of 6, so that's 2 out of 3 if you'd like. And there's 2 defective ones, so that's 2 out of 6 or 1 out of 3. If I picked a defective one first, I still have all 5 of my working ones. So I'm going to have 5 out of 6 and 1 out of 6. If I got a working one and then a defective one, I still have 4 working ones, and I'm down to 5 bulbs in my box. And I have 1 defective one out of 5. Okay. A working one and defective one, these are going to be the same. So there's 4 working ones left and 1 that doesn't work. If I got 2 defectives, then all of these other ones actually, the probability is 1, because I know that I have to get one that works because I'm out of defective ones. So it's a little bit of a weird tree because it stops at weird times sometimes, but that's what we're doing. So now we want to use this tree. What is the probability at least 1 bulb, 1 defective one will be found? So we want the probability of at least 1 D. Okay, now if you look, there's lots of D's up here. In fact, every path except 1 has at least 1 D. So what I'm going to do is use the complement. So this is going to be 1 minus the probability of no D's. Okay, so that's 2 W's in a row. That's only the one path. So this is 1 minus 5 over 7 times 2 over 3. Okay, so that's going to be 10 over 21. So 1 minus 10 over 21 is 11 over 21. Which, if you like decimals, is 0.5238 approximately. Now, what is the probability exactly 1 defective bulb will be found, given that you know at least 1 is defective? So here we want the probability exactly 1D, given at least 1D. So again, I use the conditional formula. So exactly 1D and at least 1D over the probability of at least 1 defective, which we just computed. Okay, so that we know the bottom is going to be 11 over 21. The top, we've done this a couple of times now, so exactly 1 defective and at least 1 defective. I have to get exactly 1 defective, and if I do, that means I got at least 1 defective. So this probability, I'm going to write it up here, is the probability that we get exactly 1 defective. Okay, now to compute that, we're going to go up to the table here, and we're going to look for all the paths that have exactly one D. Okay, so I see this path where I got a working one, and then a defective, and then a working. Or I could have got a defective, and then 2 workings. And those are the only 2. Because I can't get any more defectives, and I can't get 2 working because then I stop and I don't actually get the defective one. Okay, so there's only 2 paths, and we just multiply along those paths. So we're going to have 5/7 times 1/3 times 4/5 plus 2/7 times 5/6 times 4/5. Okay, so both of these on the top actually are 4/21. And we know the bottom is 11/21. So you end up with 8/11, which is approximately 0.727. Okay, now I'm just going to highlight. So these 2 are the 2 yellow paths up above, so that we know for later. Okay, couple more. Suppose in Gotham that 10% of people have some sort of superhero power. Okay, I'm going to call H the event has superhero power. Okay, and there's a test to tell whether or not they have a superhero power, but it's not perfect. So it has a false positive rate of 4% and a false negative rate of 2%. And we're going to select one person from Gotham at random. Okay, so in our tree diagram, we need to know whether or not they are a superhero. I should have said we're going to select one person at random and test them. Okay, so we need to know whether or not they're a superhero. So H or H complement. And then we need to know their test result. So either they test positive or they test negative. Okay, so this is the test. This is the power or not. Okay, so this is the true value. So 10% of people have some sort of superhero power. So the probability that I get someone that's a superhero is 0.1, which means 0.9, the probability is not a superhero. Now, so false positive rate means that it's positive, that we want the probability the test is positive, but it was wrong. Okay, so it's positive, so that's going to be either here or here. Now this one, it was a correct positive, so it's going to be the one below. Okay, so that's this spot here, so that means that this is going to be 0.04. Okay, the false negative is that it's negative but false. So that means that they were a superhero, but they got a negative test result. So that's going to be 0.2. And then we can fill in these other ones by because they have to add to 1 with the other. Okay, so there's our tree diagram. Now, given that the test was positive, what's the probability they had a superhero power? So we want the probability of H given a positive test. So that's the probability of H and positive divided by the probability of positive. Okay, so when we're doing this, I guess I can use these colors. Okay, so H and positive is that branch there. Okay, and if we want positive, we're going to have to take that branch, so the same one, but also this branch down here that ends in positive. Okay, so this is going to be 0.1 times 0.98 divided by 0.1 times 0.98 plus 0.9 times 0.04. Okay, so if you compute that, you get 0.098 over 0.184, okay, which is approximately 0.7313. Okay, one more. So, every morning Aladdin goes to the market to steal himself some breakfast. On any given day, there's a 30% chance that he will want to steal bread, 50% chance that he will want to steal cantaloupe, and a 20% chance he wants to steal milk. Okay, so let's let B equals steal bread. Okay, I'm going to call it F for fruit. Okay, for the cantaloupe, and then M for steal milk. Okay, now if he tries to steal bread, there's a 20% chance he'll get caught. So C is going to be gets caught. Okay, if he tries to steal fruit, there's a 10% chance he gets caught. And if he tries to steal milk, there's a 15% chance he gets caught. So these caught probabilities depend on what he tries to steal. Okay, so we need to know what he's trying to steal in order to know the probability he gets caught. So we're going to do the stealing things first. Okay, so he might steal bread, he might steal fruit, or he might steal milk. Okay, so this is what he steals. Okay, and then after that, we're going to know, did he get caught or not? So C or C complement. Okay, so some probabilities. So we know 30% he wants bread, 50% he wants fruit, and 20% he wants milk. If he tries to get bread, there's a 20% chance he gets caught. If he tries to steal fruit, there's a 10% chance he gets caught. And if he tries to steal milk, there's a 15% chance he gets caught. So then these other ones are going to be 0.8, 0.9, and 0.85. Okay, so there's our tree diagram. Now, if Aladdin gets caught stealing, what's the probability he wanted to steal milk? So this is the probability of M given that he got caught. So that's the probability of M and C over the probability of C. Okay, so M and C is just this branch here, but C is 3 different branches. Okay, so we want to add up all those branches. So we're going to have 0.2 times 0.15 divided by 0.3 times 0.2 plus 0.5 times 0.1 plus 0.2 times 0.15. Okay, so if you simplify this, I think you get 0.03 over 0.14, which is approximately 0.2143. So there's about a 21.5% chance that if he got caught, he was attempting to steal some milk.